Hi everyone and welcome. In this video I would like to demonstrate stochastic variational inference with Pyro. So for this we're going to jump right in and see the code of one particular Pyro application that runs exactly the same examples as we've seen before. So we open the file Pyro SVI1 and we see now the code that's interesting for us. So in this example, we're going to use the stochastic variational inference module of Pyro, or SVI. And the big difference with the NUTS module is that we have a model here, but we also have a guide. And that guide function here is really critical to understanding what happens in SVI. The SVI method, or the elbow method, is based on the idea that we're not going to guess or to sample from the posterior distribution, but we're going to approximate it. And the approximate of this posterior distribution is this guide function here. So we first define a model, which is exactly as we've seen before. This is what says what the prior beliefs are and what happens when we observe something. And the guide here specifies what we would like the approximation to be. And finally, at the end of the script, we have this optimizer bit here that will allow us to run the SVI module. So this particular model is the one with the coin. We first have import torch and import pyro as usual, and then we have the definition of the model, which is exactly as the one that we have seen in the other example with pyro. So here there's no change. We first draw at random a prob parameter here, which is a uniform value between 0 and 1. Once we have done this, we flip a coin, which has this particular bias here that we call prob. So we have seen this before. We have an obs keyword here that specifies that this particular variable here is observed. So that's it for the model. We've seen that before. Now the new thing is that we also define a guide. So the guide, remember, this is an approximation of the posterior distribution. So the posterior distribution of flip does not really exist. Here this variable is observed, so we don't really need to have a posterior distribution. The only variable that we care about is the one that is not observed. This is prob. This is the latent variable. So here, to find the approximate posterior distribution of prob, we need to make a choice. And we choose this distribution to be a beta variable. Why? Well, just because theory says so. So I'm going ahead and I'm defining two parameters that I'm calling A0 and A1, and they will be the key parameters of a beta distribution. So the first thing that happens in the guide is that we need to define these parameters with pyro.param. And we need to register these parameters with a particular string here that will be the way that Pyro knows about them. So for instance, the way I define A0 is with pyro.param. I'm calling it A0 so that Pyro knows it as A0. Next comes the initial value that I want to put inside it. So this is 1 here. And finally, I define the constraint that applies to it. So this is constraint equals torch.distributions.constraints.positive. It happens that for the beta variable, we can only have positive parameters. So this ensures that Pyro is not going to try some negative values for which the distribution is not defined. We also define A1 here, which is pretty much the same as A0, same initial values here, and we just register it as A1. Once this is done, we specify how we want to sample prob in the posterior distribution. So this here in the model is the prior distribution. This describes the knowledge I have about prob before anything happens, before I even start collecting the data. And this here in the guide just specifies the kind of distribution that I'm interested in. So this is here a beta distribution. So I'm constraining the posterior of prob to be a beta distribution. But within these constraints, I'm just saying you can choose any parameter you want, A0 and A1, and pick the ones that will make the posterior distribution as close as possible to the real one. And this is using the elbow trick. So to do this, I will just define the prob sample here the same way as I defined it in the model. And it is important to realize that this prob here has to be the same as this prob there. You have to register the same name for both samples. You don't have to call the variable the same way here. You don't even have to call the variables at all, but you have to call the name that they're registered in Pyro exactly the same, so that Pyro knows that this is the way you want to replace prob here in the model by the posterior distribution. And we just say that we want a Pyro distribution of type beta, and that the parameters that we want are A0 and A1 that have been defined here. And that's it. We have everything we need now to have a SVI inference. So the model here is the initial distribution, and the guide is the approximation to the posterior distribution. And the way we're going to fit the guide to the actual posterior distribution is to use the elbow. So the elbow, remember the theory, has two components. It has one component which is the guide, and one component which is the model here. So we scroll down a little bit, and we now go to the part where we will actually trigger the inference with the elbow method. So we first need to define an optimizer here, and we're using the pyro.optim.atom optimizer. This is one of many types of optimizers that exist, and this is by far the most popular at the moment. Another example is SGD for stochastic gradient descent, but atom is much more efficient than SGD, even though it's a little bit more complicated. So when we call the optimizer here, we need to define it with a critical parameter which is LR, the learning rate. And in this particular case, we guess that a value around 0.05 is a good starting point. In general, you should start with something around 0.01 or 0.05 and maybe try smaller values here. When this is done, we create an SVI object which has class pyro.infer.svi in capital letters. And in this object, we need two items, the model and the guide. One third item is the optimizer here that we have just defined above. And we need to specify the kind of loss that we want. And we want what is called the trace elbow. This is one of the many ways that Pyro can compute the elbow. And that's the one that we're going to use all the time, the trace elbow. Once we have defined the SVI object here, which is the optimizer that will run the elbow inference on the guide, then we create a for loop here with approximately 2000 iterations is a good ballpark estimate. And we run the command this way, svi.step, and then we put inside here the data that we want the guide and the model to receive. So we're going to scroll up again to the model and the guide, and I would like to draw your attention on the fact that both the model and the guide must have the same parameters here, which means that, for example, here we're using x equals none. It has to be x equals none. Even if the guide does not use this x here, you can see that x is the value of the observation, so the guide has no use for it because it is concerned only with the unobserved variables. So we now scroll back to the SVI loop here, and you can see that when we call svi.step, we're going to pass this particular value of x here, which is torch tensor 0. So we're specifying that the value that was observed for the coin flip is 0, or tails. So this is exactly the same case as we had seen before, except that this time we're running the inference with the elbow method instead of nuts. Finally, we have a couple of printouts here that will just show the values of the parameters that we have estimated, and that will give us confidence that we have actually made a good job. So the approximate posterior distribution of prob is beta A0, A1. This is actually what we enforce here. We have chosen this in the guide, and A0 and A1 will be discovered by Pyro for us. So once we have run the 2000 iterations of the SVI, we can call A0 and A1 from the param store. And the way to do this is to say pyro.param and then the name of the parameter here. And then we print their values. What we can also do is to use these values to create some new samples from the approximate posterior distribution. So we know, or we have chosen, that this would be a beta distribution. So now we can recreate this distribution here with parameters A0 and A1 and sample as many elements as we want from it. So in these very last two lines, we're sampling from a torch distributions.beta with the estimated parameters A0 and A1, and we're taking a sample of size 100,000. This is much more than what we could do with nuts, and this will run much faster because this is a very simple simulation here. And finally, we take the mean so that we can approximate the average of this distribution to make sure that this is close to what we predict based on the theory. And finally, the last line prints the value that we have observed. Okay, so let's see how we can run this program in practice. We just need to call Python with the name of the program here, and it takes a few seconds to run the entire inference. It usually runs faster than nuts. In this particular case, it's not going to be very visible because the examples are quite small. But if you have a huge problem, the speed up is really impressive when you use SVI compared to nuts. So we see here that the values of A0 and A1 were approximately 1.2 and 1.9, and the expected value that we get is 0.38. In reality, the estimates should be 1 and 2, and the expected value should be 1/3. We have seen that the actual value is 1/3 here in theory. So we get something quite close, but there's quite some wiggle room here between A0 and 1 and the expected value. And this is because SVI is fairly approximate. We're using 2000 iterations of an algorithm which is quite approximative. And so in the end, we have to be satisfied with relatively approximate values for all the parameters that we get. At least we get the right ballpark, and usually we do this very fast. So let us have a look at the second program. This is Pyro SVI variant 2a.py. We have here a program which is the same example as last time, running with the Gaussian variables. So again, we have import Pyro and import torch. Then we have the definition of the model here and the definition of the guide. There's not much difference compared to the previous example. We see though that the model is not exactly the same as when we use nuts here. So we have the definition of mu, we have the definition of x here, and we see that there is this one extra line which says with pyroplate mu replications x.shape 0. So I'm not going to focus on it right now, I'm going to come back to it later. So for now you can just assume that this doesn't do anything interesting. So consider that the model that we have here is pretty much the same as the one that we had when we used nuts. So let's focus on the guide for now. We see that we have to approximate the posterior distribution of the only latent parameter, which is mu here. The observed variable, x, do not need to be approximated. We know their values. They are not part of the posterior distribution. So to approximate the posterior distribution of mu, we're going to use the Gaussian distribution. And we know that this is not an approximation. The theory tells us that in this case, the posterior distribution of mu is actually a Gaussian distribution. So to define a particular Gaussian distribution, we need two parameters, the log and the scale parameters. The log parameter is really the expected value, the one that's at the center, and the scale parameter is the standard deviation. So here we instantiate two parameters. Log is a pyro.param. It's registered with the name log here for Pyro, and its initial value is 0. You can see here torch.zeros, and we want one value in the tensor. For scale, it's pretty much the same story. This is registered as a pyro.param with the name scale here. The initial value is 1. You can see that this is torch.ones with only one value here. And remember that variances, standard deviations, etc. are always positive. So we need to add one element that says that constraint equals torch.distributions.constraints.positive. And once again, that will prevent that Pyro tries to allocate to that particular variable a negative number for which we cannot compute the probabilities. And when this is done, we just sample mu again and pay attention to the fact that here mu has the same name in the guide and in the model. This is important so that Pyro can match these two samples together and that it knows that it has to now replace mu with a pyro.distributions.normal distribution of which the parameters are log and scale, these two parameters that we have here. So we are saying here that we constrain the posterior distribution of mu to be a Gaussian, to be a normal distribution. But within that constraint, we're going to find the parameters log and scale that maximize the match with the actual posterior distribution of mu. So this is very similar to what we had in the previous case. We have a model, we have a guide. The model has some observed parameters. The guide does not, but it specifies the distribution that we would like to use to approximate the posterior distributions of the latent parameters, the ones that are not observed, like mu here. The one thing that we need to comment now is this line, which is with Pyro plate mu replications, and then x.shape 0. So what are Pyro plates? They indicate that some parts of the sample have to be independent. This was not exactly the case for nuts, but with SVI, when we use Pyro, this is absolutely important. This is not optional to put these plate statements here. So what does that mean? It means that once you have sampled mu here, you're going to keep the same value of mu, and you're going to sample new values of x, and that these values of x are conditionally independent with respect to each other. That means that every value you plug into x, the value here of the observations, will have to be independent of the others. We give a name to the plate, and here the name u replications is not correct. It should be x replications. So what we want to replicate here in this plate is x, the fact that we observe x multiple times. This is really what a plate means. It means that the multiple observations of the same object here, x, are independent of each other. And we have to specify the number of observations that we have, and this in general is in the shape parameter here, the shape attribute of the tensor. And at position 0, that's the first dimension, that usually corresponds to the number of observations that we have. So we are specifying that whatever number of elements are in X in this particular case, these are independent observations of the variable X. This here, I repeat, this is mandatory in SVI. You do not have to do this in nuts, but in SVI you have to do it. You can call the plate the way you like, it's not that important, but what's critical is that if you have a plate in the model and in the guide, it has to be called the same, as long as it corresponds to the same object, of course. So for now, we're just going to go ahead with this without spending much more time on this Pyro plate, but bear in mind that this is important to think really hard about the Pyro plates whenever you design a Pyro model. Let us now go to the end of the script. We're going to the optimizer part here, and lines 33 to 39 are exactly the same as they were in the case of the coin flipping, so we're not going to spend much more time on it. We just define here an SVI optimizer, and in the end of the script, we run it in a very similar fashion. We have the for loop here with 2000 iterations. We have the svi.step command here that invites Pyro to run the inference, and we're telling that the observations, the way that it should replace x here, is with these values, 1.2, 2.3, and 0.9. So this is why we need the plate statement in the model, is because we have multiple observations here of x, and we need to specify that they're independent of each other. Otherwise, you could not really compute the elbow. At the end of these 2000 iterations, we have now the log and the scale parameter that are ready for us. They have been optimized, so we can call them with pyroparam here. We can print them, and of course, we can again run a large sample where we use the normal distribution here with whichever value of log and scale we have found. This particular example is not as useful as the previous one because in principle, the average of a Gaussian sample is equal to its log parameter here. We are doing it anyway so that you can see how to do this in other cases. So let's go ahead and run the program to see how this happens in practice. Again, we just need to write Python and then the name of the code here, and that takes a few seconds to run. So we see that the log parameter here is estimated to be 1.24 and the scale parameter is estimated to be 0.61. The expected value here in the last example that we ran is 1.24. So again, the estimates are not exactly spot on. Remember that log here should be 1.1 and scale should be 0.5. So why is that? Again, running only 2000 iterations is maybe not sufficient, and we haven't taken the best precautions to make sure that the inference runs very smoothly. But still, that gives us a good approximation of what the values are and where we can start to think about the posterior distribution here. Let's have a look at the last example for this video. So this is Pyro SVI variant 2b.py. Here we can see that this is the same model as in the previous example. The main difference with the previous script is that the guide has almost completely disappeared. It is just one line here at line 16. So there's no other modification here in this particular script. The model is exactly the same as in the previous example, but you can see that the guide now consists of just one line. So it's important to realize that Pyro offers you the possibility of writing the guides for you. So remember, the guides are the approximations to the posterior distribution. And Pyro offers that it will approximate automatically the posterior distribution with just a family of variables that you like. So for instance, we can say that we want to approximate every latent variable in the model with a Gaussian distribution. The way to do this is to say guide equals pyro.infer.autoguide.guides.autonormal, and then we pass the name of the model. When we do this, Pyro automatically creates a guide where the parameter mu here will be sampled from a Gaussian distribution. So this is exactly the same as in the previous example, except that in this particular case we do not have to write the guide. Pyro can do this automatically for us, and in principle, because we had requested that the posterior distribution should be Gaussian, we're going to obtain exactly the same when we use the auto guide here. The rest of the program is pretty much the same. There's no difference here on the optimizer or the SVI definition. There is no difference here in the training loop. The only difference that we have is in the name of the parameters. So because we have not defined the guide ourselves here, we just have to refer to the standard way in which Pyro allocates the names for the parameters. So lock is now called autonormal because that's the way that we define the guide here, and then locks for the location parameter, and mu because that's the name of the parameter that I want to infer. And scale is called the same way, where you replace logs by scales. Even if there is only one value here, it's always put in the plural because in general you have more than one value. So that's one thing that's important to know, is that in this case the parameters will be called this way. There is always a log parameter and a scale parameter because every parameter is, like mu, is estimated with a Gaussian. And there's no difference for the rest here. We just print log and scale, then sample 100,000 elements from a new Gaussian distribution, and we print the average. So we should obtain exactly the same as before, of course, up to the random variations that exist between the different runs. Here we go, these are the results. So we see that the log parameter is estimated at 1.19 and the scale is estimated at 0.57. Again, the theoretical numbers should be 1.1 and 0.5. So we're not very far, but we're not exactly spot on either. We would need to run a little bit more carefully this simulation if we wanted to get exactly the right result here. Still, it's interesting that we're only within 10% of the actual numbers here. So this is it. Those are the different ways that we can run Pyro for stochastic variational inference, or SVI. The main feature of this approach is that we need to define a guide, which is an approximation to the posterior distribution. And of course, this guide needs to be fitted so that it matches at least approximately the posterior distribution. For this, we define a couple of parameters, and these parameters are updated at every cycle of the training loop. So this here, in a nutshell, is the way that we can run stochastic variational inference. The main advantage over NUTS is that it is much faster when the problems are very large. That's it for this video. More from me soon.